Hello, everybody. Today we start with the last chapter, chapter 8. It is about adjoint, self-adjoint, and compact operators. Of course, there are many fat books about the theory of adjoint, self-adjoint, or and compact operators. And the aim of today's lecture, this week, the lectures of this week, is just to introduce the basic notions and to speak a little bit about the properties and what it is all for. No more. Then you have to read the books to get more rigorous theory. Okay, so we start from the very beginning. We define all the objects we are going to discuss. And we start with adjoint operators. So, definition 8.1, let X and Y be norm spaces, and A be a bounded linear operator from X to Y. The adjoint operator to A is denoted by A star, and it is a mapping from Y star, that is the topological dual to Y. From Y star to X star is the topological dual to X. And it is defined in the following way. We will clarify this formula in a second, but first a picture that X and Y, so A maps X in Y, and the adjoint operator lives somewhere else. Not here, but so to say on another level. And it is the mapping between topological duals, but not from X to Y, but from Y to X. Okay, so this is the formula, so how it acts. We take, so A star is a mapping from Y star. So Y star is a continuous linear mapping on Y, functional on Y. So A star applied to Y star, according to this, it should be the element of X star, that is a continuous linear functional on X. So this continuous linear functional on X at the point X is defined in the following way. So this is Y star evaluated at the point AX. So if X is here, so probably I can make a picture. So if my point X is here, so here my point AX, it is in Y. And I can evaluate at this point the continuous linear functional Y star, which is a continuous linear functional on Y. Okay, so let us discuss this definition in more details, namely. So first of all, from this formula, it should be obvious that A star is a linear mapping. That is, if instead of Y star, we consider linear combination of two different Y stars, then due to the right-hand side, you see that the linearity is satisfied. So is it clear?
Yes.
Okay. Second, let us check that this formula really gives a mapping from Y star to X star. So the statement is that this object is indeed not only linear but continuous functional on X, because this formula, what this formula means? This means that this is nothing else but a composition of A and Y stars. Yeah? But since A and Y star both are linear and continuous, then their composition is again linear and continuous. Hence, we have this statement. Is it clear?
Yes.
Perfect. Well, then we go further. And the second statement, so one more statement is that this mapping A star is not only linear but also bounded linear mapping, bounded linear operator. And the operator norm of A star is not bigger than the operator norm of A. So indeed, let us check it. So what is the absolute value of A star, Y star evaluated at the point X? So it is as here. So By this formula, we know that this is as in the right-hand side. So this is absolute value of y star at the point ax. But y star is a continuous linear functional, so we know the following estimate, so standard estimate, which we have used many times during the lecture. So this is the norm of y star times the norm of this vector ax in y. And now again, we may use similar inequality. This is y star, norm of y star in y star times the norm of a operator, norm of a, times the norm of vector x in x. So having this, we see that the norm of the linear functional a star, y star, it's a linear functional on x. So by definition, the norm of linear functional is supremum over all x's from bounded, from closed unit ball of such things. And this is smaller or equal than norm of y star in y star times the operator norm of a. So from this, you see that the norm of a star, operator norm of a star, which is supremum over all y star, is smaller or equal than the norm of a. And this means that the operator a star is bounded linear operator. Okay, everything is clear. This was my question.
Yes.
Perfect. Well, actually, we have more. We have not inequality, but equality. And this we are going to show in the next slide. So may I go to the next slide?
Okay, please.
Perfect. So theorem 38. So the mapping, which maps A to its adjoint. So it is then the mapping between spaces Lxy and Ly star x star. So this mapping is a linear isometry. That is, for any two elements A and B from this space of bounded linear mappings from x to y, we have that the norm of A star is equal to the norm of A. Adjoint to a sum of operators is the sum of adjoints. And if we multiply an operator A with a scalar lambda from our field scalars and take a joint, then it is the same as we just take a joint of A and then multiply with this scalar. Caution that this mapping, so let me specify the mapping. So this mapping in general is not surjective. What does it mean? This means that if we go to this picture, so there are some operators acting here, like operator B, such that there is no any operator here, such that this B is adjoint to this one. Okay, so the space, yeah, so this space may contain, so to say, more elements than this space. So isometry, but not necessarily isomorphisms. Also take it into account. So this is one statement, that this mapping is linear and isometry, that is the norm is preserved. And the second statement is that if we have free norm spaces and we have, okay, x, y, Z, and we have two mappings, A from X to Y and B to Y to Z, from Y to Z. Then we may consider composition. It will be the mapping from X to Z. And then the adjoint of this composition is the product, composition of adjoints. But you have to be careful with the order because, again, here we have this picture on another level. So B acts here, B star, and A star acts here. So in order to make a composition from X to Z, you should take first B and then A, if I'm not wrong. Yes? Yes. Or I'm wrong with the A from X to Y, B from Y to Z. So I guess here may be something wrong in the sense that probably here should be BA, yes? No. Yes, BA. We first act by A and go to Y. And then we go to Z by B, yes? So this is the matter of notation. So you first act by A and then by B. And here, in order to get this mapping from Z star to X star, you first act by B star, and you go here, and then you act by A star and you go here. Okay? But probably this notation, what does it mean? So let me correct like this. BA star is A star, B star. Yeah? Am I correct?
Yeah, I think it's BA, not AB.
Yes, it was a typo. Okay, so pictures sometimes help to find typos. Okay, so these are two properties which we are going to prove. So actually a part will be given as an exercise, but let us prove this statement that the mapping is a linear isometry. Okay. So we start our proof. We prove part 1. So by remark 8.2, we know that the norm of A star is smaller or equal than the norm of A. So now task is now to prove the opposite inequality. So let us show it. So not otherwise, on the other hand, for any epsilon positive, there exists an element X in the space big X with the properties that the norm of X is equal to 1 and the norm of AX in Y is bigger or is strictly bigger than the norm of A minus epsilon. So this follows from the definition of operator norm as supremum. Hence, if this is the supremum over such things, then I can choose in this set of such things where X satisfies this identity. I can choose one element such that we are not far away from this supremum. And this can be done for any epsilon. So is it clear?
Yes, it's clear.
Perfect. Now we, of course, use corollaries from the theorem of Hahn-Banach. Namely, we will use by corollary 513 of Hahn-Banach. Theorem. So what kind of corollary it is? I guess I have it. It is lecture 11. Let me check. No, it is lecture 13, 14, 15, 12, 11. Yeah. So corollary 513 it says that for any point of a norm space, we can find a continuous linear functional in this space such that at this point, the value of the linear functional is exactly the norm of this point, and the norm of this linear functional is 1. Okay, do you remember this corollary?
Yes.
So good, then we use it. So by this corollary, so we take this element, this is y, lives in this space. So by this corollary, there exists a linear function, continuous linear functional y star, such that the norm of this continuous linear functional is 1. And and this absolute value, so by definition of A star, this is nothing else but the value of linear functional y star at a point ax. So we can find such a linear functional that its value at a given point is just exactly the norm of this point. That is this guy. And we know that this guy is bigger than the norm of A minus epsilon. Okay. So what we have that this is bigger than norm of A minus epsilon. So hence the norm of A star, the operator norm of A star, it is supremum, by definition, supremum over all y star norms of y star small equal to 1. And here supremum over such objects. But this guy is itself a supremum over all x's in x, norm small equal to 1, and supremum over these things, A star, Y star evaluated at x. Yes. And we see that this guy here is bigger than this. Hence, supremum is also bigger than this, and hence this supremum is also bigger than this. So all the story is that this is bigger than norm of A minus epsilon. Yeah. So norm is bigger than norm of A minus epsilon, but this happens for any epsilon. So hence, norm of A star is bigger or equal than norm of A. And we have shown the opposite direction. We have this and we have this. Okay, so we have shown that this holds. This means that this mapping is an isometry. And now all the rest is the exercise. So this is simple, and this is also simple. Yes, but with the proper formulation. Okay, so may I go to the next slide?
Okay.
So let me first specify that this and this it would be an exercise. Okay. So we have shown the isometry. All the rest is a home task. Okay, so now we go to examples. So example 8.4. So just to remember, this was the definition. I just preserve it so you can see the formula anytime you need. So we start with the first example where X is Rn, so finite dimensional norm space, Y is Rm. Then we may associate X star, so topological dual, with its algebraical dual, and it is Rn. And the same for Y star, so the topological dual is equal to algebraic dual because all linear functionals on finite dimensional norm space are continuous. So the topological dual is again Rm. So let me recall how we do all these associations. So we discuss now this line. So recall that if we have X, let me work with Rm. For Rm is everything the same. Hence, we may consider orthonormal basis there. It is there are finitely many vectors. Hence, any element X in X can be represented in this way, Xi EI. So it has its coordinates in this basis, and they are unique. So for each element of our space, we have this decomposition in a given basis, and we have hence the vector in Rn, vector of coordinates. Now we take a linear functional, so consider L in X dual, topological dual. Hence, when we evaluate at the point X using the linearity, it is sum I from 1 till n xi L of EI. And hence, we may associate L with the vector of coordinates L of EI, E1, etc., L of En. And this is again a vector in Rn. And this is exactly the way how this topological dual is as identified with Rn itself. And since we have X and X star and Y star, so instead of using the notation L for linear functionals, we use more suitable notation that linear functionals on X are denoted by small x stars, and linear functionals on Y are denoted by Y star, small Y star. Okay, so we have this. And then any linear mapping from X to Y in the same ONB is given by a matrix. So now we would like to understand what is A star. So I write down this formula as in the definition. And now I remember that X is a column vector, as here. A is a matrix if we work in a given ONB. So here we have a matrix times vector. It's a column vector in Y. And what is given here? So you see, as here, what does it mean? For example, here, what does it mean? This means that the action L of x can be written as a matrix product. So we take the coordinates of vector L, but as a row vector. So I have to write down it like L of E1, etc. L of En times a column vector x1, xn. So it's a matrix product. So again, here we have a vector in y, and we evaluate continuous linear function on this vector. So we can rewrite it again as a matrix product. So I need, this is a column vector, and this is a row vector. That's why I use this notation. This is for transposed. So to make a row vector from a column vector, you need to transpose it. So we have this. So matrix, here column vector, here row vector. This is the product. And now this is the same as if we first take the matrix A, transpose it, multiply with a column vector y star, then we get a column vector, and then transpose it, and we get a row vector, and multiply again as a matrix product with a column vector. So is my notation clear now?
Actually, the transpose here is a little confused for me.
Yes. So this is about matrix product. So if you have a matrix, let's say like this, you may consider product with a column vector from the right. But if you want to have so let me do like this. You have a row vector times a matrix. So the size should be appropriate. This means that this is equal to this. So if you make this product of a row vector and the matrix from the right, it is the same as you first transpose the matrix, multiply it with the column vector, with this guy column vector on the right, and then transpose everything back. So it's a matrix. It's a properties of matrix product. Okay, so what happens here? So sorry, probably I was not quite good. So we have a matrix, this one. We have a column vector x, this one, and we have a row vector y, this one. So we may either do like this. So first multiply a with x and then with y. Or we may do like this. Okay? And now I want to rewrite it in the way that I multiply something with, not from the left, but from the right. Okay? And I guess this is, roughly speaking, this is exactly this situation. Yes? So you have a product of this and this, and I want to have from the opposite side, so to say. That's why I make transpose, multiply, and then make transpose once again. Okay, so let me refer to the properties of matrix product, exercise for you, home task for you to check the rules of matrix product. But once again, this is a special case of what we of what is written here actually. where this is the transposed. Okay, sorry. I think we should not spend more time on discussing matrix product, but nevertheless, what is written here, here, and here? So my argument is X. And this is the matrix product of a row vector with a column vector. Yeah, so this is a column vector time. So we have a matrix times a column vector. It's a column vector. We transpose, we obtain a row vector, and we have a product of row vector, the matrix product of row vector with a column vector. This means that this is the action of this linear functional on element X. And this means that this linear functional is the same as this linear functional. Hence, we have clarified what is A star. A star is just A transposed. So what means this transpose? This means that my Y star, my Y star should be a column vector. And I use this transpose here to specify that this is now a row vector, not a column vector. The same is here, just to make a row from a column. Okay?
Okay, it's clear now.
Perfect. Okay, so in this nice simple case, the adjoint to a linear operator is in the same orthonormal basis is just given by a transpose matrix of A. Now we have a next example number 2. So number 1 stays with us to remember. Now example number 2. As X we consider Cn, and as Y we consider Cm. So here Rn, Rm, and here Cn, Cm. That is, in this case we had a field of scalars R, and in this case we have the same, but field of scalars is C. And in this situation, there are two different ways how we identify. So what is the topological dual to CK? K equal to N or M. So of course it is CK. So the topological algebraical dual to CK is CK. But the question is how we identify it, how we identify this space with this space. And there are two different ways. So one way is as follows. So any continuous linear function on CK can be identified with a vector A in CK in the following way. So this continuous linear functional Z star evaluated at point Z is given like this. It's a scalar product of Z and A. And scalar product in CK is given in this formula. So we have a complex conjugation here on the second argument. And this is exactly the special, what is written here. This is just exactly the special case of Riesz isometry. This is Riesz isometry. And recall that this is a nice Hilbert space. So in this particular example of a Hilbert space, Riesz isometry is given exactly like this. And then this association, so identification of this space and this space is conjugate linear, because Riesz isometry is conjugate linear. So you see here this bar. There is also another way to associate, identify this space and this space. Namely, for any continuous linear function on CK, we may associate a vector A in CK such that Z star evaluated at point Z is given like this. So it's a scalar product with A bar. And then if you write scalar product and remember this bar, then you get this formula. So in this formula, you don't have any bars, and hence this association is a linear association. Yeah, so you don't have any bars in the formula. So here we have linear, and here we have conjugate linear. So they are two different. So the question is where you like to have your bar. Here it's a nice formula without bar, but then you don't have a scalar product. You have scalar product with extra bar. And here you have a scalar product as it was in the Riesz isometries. So also natural. Okay, so is it clear about these two ways to identify this space and this space?
Yes.
Perfect. And depending on the choice of this identification, of course, in both situations for X and Y, the same type of identification. Then, depending on that, we find a star. We find it exactly in the similar way as here. That is, each linear operator between X and Y is given by a matrix in a standard basis, and then we make similar calculations and we obtain the following. So in the first case, we obtain that the adjoint is A transposed and here complex conjugation. In the second situation, the adjoint is given by just A transposed. So here just transposition and here extra complex conjugation. Okay. So it's a very small thing which says that you should be careful where you have your bars. So either you have your bar here and then not here, or you have your bar here but not here. Okay. We have no time to discuss all this and proceed all the calculations, but they are elementary and I hope you can check yourself. So doing exactly as here, you can check that this holds. Okay, so may we go further?
Okay, please.
Yes. Nevertheless, please remember this small fine thing which appears when we consider complex numbers. Okay, so part 3. Now let X be a norm space, Y is equal to X. Then the complex, so the adjoint operator to the identity operator on X is just the identity operator on its topological dual. So let us show it. So indeed, so for any Y star, so I use this, I want to use this formula. So for any Y star in big Y star, and for any X in X, as we have here, we have the following. So I try to write down this left-hand side. So identity operator in X, it's adjoint, applied to Y star and evaluated at the point X is equal to, so I use this formula. So the left-hand side is equal to the right-hand side. So the right-hand side looks as follows. So it is Y star at identity X applied to X. This is, however, Y star at the point X. And now this Y star I can rewrite as identity in Y star applied to Y star at the point X. So I have used here y and y. So I have used y just to mimic this formula, but I remember that y is equal to x, yes? Okay, perfect. So let us go further and consider one more example. Example 4. So now p is from 1 to infinity without infinity. X is equal to y and is equal to LP space of sequences. And x is just an element of LP. So these are the coordinates of this sequence in LP. So we consider two operators, left and right shift operators. So left shift operator acts as follows. It takes element x from LP, kill the first coordinate, and all other coordinates will be shifted to the left for one position. That's why left shift. And as a result, we obtain these coordinates. How acts right shift operator? It just shifts all the coordinates to the right for one position, and hence the first position becomes free, and it puts 0 as a first coordinate. Okay, so is it clear how it works?
Yes.
Yes. So hopefully it is quite easy to see that both operators, they are bounded linear operators for any p from 1 till infinity without infinity. So just recall that I guess I told about this, but I didn't written it in a Solon form, that if I use this notation, this is the set of bounded linear operators from x to x. Oops. This is the notation which I used here. Okay, so actually the norm of each operator is 1, but this is an exercise for you to check. And what we are going to do now, the statement is that the adjoint to SL is the operator SR. So adjoint to the left shift is the right shift. Then it acts on a joint space, dual space, 2LP. And we know that for such P's, the dual space to LP is LQ, where Q satisfies this condition. Yes? So this is the statement. Let us check it. So indeed. So for any y star, which is the element of topological dual to LP, but we know that this is LQ, isomorphic to LQ. And for any x in LP, we have, so I have taken this y star from y star and x from x, and I use this formula. So I'm interested in topology, in adjoint to SL. So SL star evaluated at y star. This is then at the point x. So as it's written here, it should be given by the right-hand side. So it is a y star at the point SLX. And now I use, so I know how continuous linear functionals acts on LP. I know because it was a theorem. So this is a theorem 612. So let me find, I guess I have it somewhere. No. Oh yeah, so let me, yeah, 612. Theorem 612. So we have P from 1 to infinity or P equal to 1. then all continuous linear functionals look as follows, so act as follows. Yeah, the formula is always the same, and these A coordinates A, they correspond to the vector in LQ. Okay. I hope that you remember theorem 612.
Yes.
Yes. So let us use it here. So this acts as follows. It's a sum j from 1 to infinity. We take the vector SLX, take it j's coordinate and multiply with y star j. So I mean here that y star corresponds to a vector in LQ, and this vector has such coordinates. Okay, so now we may change how we calculate this. So first of all, we know how SL acts. That's why this is the sum j from 1 till infinity. So if I act by SL on X, I have this formula. Hence, j's coordinate of this guy. So if this is my X, this is my SLX. So what is the j's coordinate of this vector? This is my question to you. So what should I write here? What is the j's coordinate of this vector?
xj plus 1.
Yes. Xj plus 1 times y star j. Now I change the summation index in the following way. This is 0 times x1 plus sum j from 2 to infinity xj y star j minus 1. So I have changed my summation index. Agree?
Yes.
Perfect. But then we can write it down in the following way. This is j from 1 to infinity xj times, and here SR y star j's coordinate. That is what we have here. This is the action of SR y star at the point x. Agree?
Yes.
Yes, but yes, we have shown this. Okay. For the case p equal to 2, then q is equal to p. We have that all these guys live in the same space. And we see that the composition, first right shift and then left shift, leads to the identity operator. Yes. So we take this vector, first right shift, we get this vector, and then left shift. Yeah, so everything goes to the left and the first is killed. This is the identity. But if we first apply left shift and then right shift, so we have this point, these coordinates. First apply left shift, we have these coordinates, and then we apply right shift, so everything goes back, but we have 0 as the first coordinate. So this composition is not identity operator, but actually the orthogonal projector on a subspace of all coordinates except the first one. So orthogonal projector on a space whose co-dimension is 1. Okay?
Okay.
Perfect. So this is just, okay, one of the standard examples of adjoint operators. And yeah, this is just nice to know. Well, now we are going to prove some lemma. Lemma looks as follows. We have two norm spaces, x and y. A be a bounded linear operator from x to y. Then we have the following statement. The closure of the image of the space x under the mapping A, so the closure of this image, is given in this way. That is, this is the intersection of all kernels of continuous linear functionals y star, such that y star belongs to the kernel of the adjoint operator. So here we have A, here we have A star. So this is the relation between them. And so what is written here? So this is nothing else but the set of all y's in Y, so which belong to the kernel of Y star, that is all y's of Y, such that we have this identity for which Y star, for those Y star, that is for all Y star in kernel of A star. That is the image, the closure of the image of X under A is given here, where you have here kernel of A star as a main ingredient. So let us show this statement. This is again connection between A and its joint. So first step, let Y be just AX. And Y star belongs to the kernel of A star. Then, that is, what does mean that Y is equal to AX? This means that Y belongs to AX. First without this closure, just A of X. So Y belongs to the image of the space X under A. Okay, then Y star evaluated at Y is just Y star evaluated at AX. Now, using this definition, using this, we have that this is equal to A star uh, applied to Y star and then evaluated to the point X. This is by definition of A star. But since Y star belongs to the kernel of A star, this means that this is equal to 0. So this is a zero linear functional. So this is 0 for any x. And hence you see, so that this guy, so at the moment we don't need any x, we have a fixed x. X is fixed, y is given like this, also fixed, and we have this. So you see we have this identity, and this means that such y, it was an arbitrary element of this set. Yeah, so my y of this form means that y is an arbitrary element of this set. And we have shown that for such y, we have this. It belongs to the intersection of kernels of y star over all y star in the kernel of A star. Yeah, so we have taken any arbitrary y from this set, and we have seen that y star applied to y is equal to 0 for any y star here. This means y belongs to the kernel of y. And this happens for any y star from this set. Okay?
Okay.
Okay. So y stars are continuous linear mappings, continuous linear functionals. So their kernels are closed subspaces. And hence the closure of closed, not the closure, the intersection of closed sets is a closed set. So since this set is closed, we have also, so since we have this inclusion, we have the inclusion that the closure of this guy lives in the closure of this guy. But since this guy is already closed, then the closure of this guy is just this guy itself. So we have that A of X closure is a subset of this intersection. So we have shown one side. We have shown inclusion, but we want to have to show the identity. So next task will be to show the opposite inclusion. But I will do it on the next slide. May I go to the next slide?
Yes, please.
Yes.
Yes.
Perfect. So we go further. So let now y belong to this set. Let y belong to the intersection of kernels of y star. Assume y does not belong to A of X closure. That is, we assume that this set is bigger than this set. There is an element which lives here, but not here. Recall that A, A is a bounded continuous operator. Since A is a bounded continuous operator from X to Y. So A of X closure is a closed subspace of Y. I mean, here actually we don't need the boundness. We need that A is a linear operator. Since A is linear operator, this guy is a subspace of Y, and since we have the closure here, it is a closed subspace. Okay, now by corollary, again we use the Hahn-Banach theorem and its corollary. So by corollary, now it was 521. Oops. Of the Hahn-Banach. It is in lecture 12. What is it? What is this corollary about? So we have a closed subspace and a point which does not belong to a closed subspace. So we may separate. So we may separate these two objects, this subspace and this point, by means of a continuous linear functional. So this was the statement of this corollary. So by this corollary, there exists a continuous linear functional y star with the following properties. So y star at y is equal to 1 and y star on this subspace is equal to 0. That is, this continuous linear function separates the point and the space. Okay? Then, for any x in x, we have the following. So a star, y star at the point x, this is, again, by definition of the adjoint operator, this is y star at the point ax, but this point belongs to this set, and hence y star evaluated at this point for this particular y star gives us 0. So this is 0. Yeah? So for exactly this y star. Due to this assumption, we have this. But what does this mean? This means that y star belongs to the kernel of the mapping A star. Yes? From this, for any x, we see that this is a 0 linear function. And hence this is, so y star belongs to the kernel of A star. But this means that y star evaluated at y, exactly this y, which we used here, should be equal to 0, since my y, oops, something going wrong. Since my y belongs to this intersection of kernels. Agree?
Agree. Yeah.
But then we have a contradiction because what? Because we have this and we have this. That's it. Hence our assumption that this set is bigger than this set and there is something which lives here but not here. Our assumption was wrong. Okay, so we have shown this nice identity. It's a relation between A and A star. Please remember this. We will use some consequences of this fact a little bit later. And now let me go further, if you don't mind.
Okay, please.
Yes, please.
Perfect. So remark, so let X be a norm space. So this is again the definition of a joint operator. Let X be a norm space. And now we make the following, okay, changing of notations, let's say. We consider the mapping, denoted as bracket, where first argument is from X, second argument is from X star, topological dual. This is mapped to K, and this mapping is defined as follows. So brackets X, X star is defined as X star evaluated at the point X. And this is the definition for all x's in X and X star from topological dual. So this mapping is called duality between X and X star. And on the level which we are interested in, so far this may be considered just as the changing of notations. So instead of writing like this, we may write like this. Because actually this means that we consider x as a point, x star as a linear function, continuous linear functional on x, and this is the evaluation of this functional at this point. But on the other hand, what stays here can be understood as the following. This is gx at x star, where gx is the linear functional on x star, which is just the point evaluation. So we take this linear functional as an element, and so application of this continuous linear function at this element is just the point evaluation at the point x. So in this notation, this means that x star is now an element, and this, or x itself, is considered as a continuous linear functional here. So this notation just makes these two elements like they have the same role, how to say, not the same role. So here you do not specify what you consider as a point and what as a continuous linear function. So you may change the roles. And in the sense, they are equally, oh God, my English is not that good, but I hope you understand what I mean. So this is a notation, a kind of a symmetrical notation where you may play what is your point, what is your linear function. Okay, please pay attention that since this left-hand side is defined via this right-hand side, this mapping is a bilinear mapping with respect to both arguments. So with respect to this one and this one, just due to definition. Okay, so having this new notation or this new notion, duality, we may rewrite this definition in the following form. So in terms of, I use these brackets, both for duality between x and x star and also for duality between y and y star. So then this definition, so this formula can be written in this way. So the adjoint operator is the operator such that this formula holds. Where here we have x in big X, and this is element of x star. So here we have duality between x and x star, and here this is the element from y, and this is the element from y star. So on the right-hand side, we have duality between y and y star. But nevertheless. Okay, so of course, in the special case, if x is equal to y, x is equal to y, and they are not only norm spaces, but they are Hilbert spaces, then we know how linear functional acts on a vector due to this isometry. Yeah, and this action is given by a scalar product. Yeah, that's why actually we use this notation, such brackets, which resemble very much the scalar product. So in the special case of Hilbert spaces, we may rewrite definition 8.1, and it gives us the following definition. Definition 8.7, so let X be a Hilbert space with scalar product, the same brackets, but with symbol X. And as y, I also use the same x. So I consider the mapping A, which is a continuous linear mapping from x to x. So now let phi be the Riesz isometry, as in theorem 610. I guess we have, yes, so 610, yeah? So if x a Hilbert space, then for each element v in x, this mapping is a continuous linear functional, and actually each continuous linear functional is given in this way. So this is my Riesz isometry. Okay, so coming back to my definition. So the so now I would like to define as an adjoint operator to A, but the Hilbert space adjoint. That is adjoint in the category of Hilbert spaces. So this is the operator which I temporarily, so now I denote by A star with a specific star. And this is the mapping which acts again from X to X, so on the same space X. And this operator is defined by the following formula. So if you compare, so everything is totally the same, except that here I use duality and here I use scalar product. That is, this A star with a specific star is actually a bounded continuous operator on X, and it is defined as follows. So I take the adjoint operator in the sense of definition 1 and compose with, in a proper way, with Riesz isometry. So once again, we have definition 1. For the general case, X and Y are norm spaces. Now we consider the situation where X is not just norm, but Hilbert space, and Y is equal to X. And coming back to this situation, I may define A star as before in definition 8.1, and it acts from X star to X star. So A is here, A star is here. And now I can lift all this picture, so this level I can lift here on this level using the Riesz isometry. So that's why having A star here on this level, I now come to a specific star which acts on the same space as A itself. Okay, so this is one thing. So in the special case of Hilbert space, using Riesz isometry, I may make my adjoint operators to live in the same, to act in the same space where the original operators act. Okay, is it clear?
Excuse me. I want to ask where we define such a category.
Now don't use the word category in some rigorous mathematical sense. This is just a word of language.
Sorry. Okay. Thank you.
We don't need to go to the category or whatever. I mean, category theory or whatever. This is just to distinguish. So this is the general definition. Now we consider special case. And we define kind of a new adjoint operator. We should distinguish somehow this guy from this guy. That's why we call it just that this is adjoint in the category of Hilbert spaces. And so the difference is as I have specified. So A star is acting on this level, and this A specific star is lifted to the same level where A acts using Riesz isometry. Okay?
Okay, thanks.
Perfect. And now a small finite, a small technical thing, because here we have duality and here we have scalar product. If my K is just real numbers, then everything is perfect. We just make a point here and that's it. But if my K is a complex numbers, then my scalar product here is linear with respect to this variable, first variable, but conjugate linear with respect to second variable. And duality is bilinear. So this guy is sesquilinear, so conjugate linear with respect to second variable, and this guy is bilinear. And this is again this small Feinheit, Kleinigkeit in German. So маленькая мелочевка. A small tiny thing, but we should take care about it. So caution, so if K is equal to C, then my scalar product is conjugate linear with respect to second argument, whereas the duality is bilinear. So actually the definition is not totally the same. There is a small Kleinigkeit. This is exactly the same situation as we have done in the example, so in this example, 8.4. So now in the general case of Hilbert space, we use, of course, Riesz isometry, and we get this story. Okay, so we should just take in mind so that there is a small difference between adjoint in the category of Hilbert spaces and just general adjoint. And this small tiny difference is first of all the spaces where these operators live, but also in this linearity, conjugate linearity in some spaces. So the properties of this guy is a little bit different from the properties of this guy. That's why let us summarize the properties. So let X be a Hilbert space, A and B bounded linear operators on X, lambda is a scalar, then the following holds. Still, the adjoint to a sum is the sum of adjoints. But now, so this mapping A is mapped to A with this specific star. This is not a linear isometry. We have this nice, or not nice, but this property. So when you pull out your scalar, you should pull it with complex conjugation. Again, the mapping is isometry. That is the norm of A conjugate is the same as the norm of A. And we have also this nice property. So of course, if we have X and Y, and we have A acting here, we have X star and Y star, and we have A star. But this is a norm space, this is a norm space, this is a bounded linear operator acting between two norm spaces. And we may apply definition 8.1 for this new situation. Hence, we have topological dual to X star, we have topological dual to Y star, and then here acts A star, star, so two stars. Now my question is, where should I put the arrow? Here or here? This is my question.
From left to right.
Yes, exactly. Yes, and now, and now if occasionally X is reflexive, so if X2 stars is the same as G of X, hence A2 stars is just A. If X star, two stars, so topological, also B dual is bigger, then this operator lives or acts between bigger spaces. I mean, here I'm speaking about in the situation y is equal to x. So because I am interested to come back here. So I consider y is equal to x, but nevertheless, so if x is not, if x is reflexive, the situation here is just the same as it was originally. If x is not reflexive, then this space is bigger, and this guy is something bigger than this guy, so they do not coincide. Then A star, two stars, restricted to G of X is equal to A. So details you may read in the book of Conway. So actually I wanted to say you, and I have forgotten, of course, as usual. So last time we have discussed chapter 7, weak topologies. And there is, I guess, sorry. Yes. So this is a nice reference. It's a nice textbook, very roughly concise, not very simple, but still sufficiently acceptable, clear and concise. You can read about weak topologies in chapter 5. Okay. Also, what I'm describing now, you can read in this book of Conway. It is a proposition So now it is chapter 6, not 5, but 6, proposition 1, 4. Okay, this is a proposition that A2 stars. So this situation is exactly corresponds exactly to my remark that the space X star is big enough such that there exist elements or operators from X star to X star which are not topological, which are not adjoint to something from here, from this level. Okay? So coming back to remark 8.2, that this mapping A is mapped to A star maybe does not need to be surjective, does not need to be isometry. But if X is reflexive, then this is an isometrical isomorphismus, so vice versa. And we may repeat it and we may obtain this. Of course, Hilbert space is a reflexive space. And we have this in this special case. And also we have this. Because complex conjugation twice will disappear. Okay, so it was a kind of lyric. And also, this is also a nice property that composition of A and A star in all directions in different orders. So it is an operator, again, a bounded linear operator on X, and the norm is always the same and is equal to the norm of A squared. So this is a simple exercise for you to show all these things. Okay, all these things except this one. This one we have discussed a little bit. Okay, so please pay attention that there is a slight difference between such star and such star. Nevertheless, in the sequel, as soon as X is supposed to be a Hilbert space, we consider only a join in the category of Hilbert spaces. Hence, we don't need a specific symbol for this operator. And so in the sequel, we use only this symbol. So it should be clear what this symbol means, in the sense that if X is a Hilbert space, that this symbol means this. Otherwise, this symbol means adjoint in the sense of definition 8.1. Okay? Is it
Okay.
clear? Perfect. So, definition. So let X be a Hilbert space, let A be a bounded linear operator. The operator A is called self-adjoint if A star is equal to A. That is, we have this formula. So now you see you need to have A star to act on the same space. Okay, I hope this definition is clear. And let me ask you, do you know any examples of self-adjoint operators? You should know something from linear algebra, for example.
For example, you can consider Rn as a Hilbert space. Then we can consider just the matrix X on the column vector.
Yes,
Then
and then which types of matrices will correspond to self-adjoint operators? Recall that if X is equal to Rn, then A star is equal to A transpose. Yeah, example 8.4. And we don't need any complex conjugation, yeah, in Rn. So what kind of operators will be self-adjoint?
just the matrix satisfying this property, but I suddenly forgot the name of such matrix.
The others probably know the name. Okay, these are symmetric matrices. For example, diagonal matrices, yes? But not only diagonal, all symmetric matrices, so which satisfy this property, they correspond to self-adjoint operators acting in this nice Hilbert space. Okay,
Ah, yes, thanks.
perfect. Now some more examples. So let X be a closed subspace of a Hilbert space. Let Px0 be the orthogonal projector on X0. This is where it was defined. Then the operator Px0 is self-adjoint. So orthogonal projectors are self-adjoint operators. It's a very nice example. Orthogonal projector is self-adjoint. So I probably have, yes. So if we have a Hilbert space, Hilbert space, X is a closed subspace, then X can be represented as this direct sum, and that orthogonal projector acts as follows, where this Px0 is just a projection on orthogonal projection on X0, which satisfies this. Okay, so let me show. So I have shown you the definition of orthogonal projector. Now let me show that this operator is self-adjoint. Indeed, for any x and y in X. So for any x and y in X, I want to check that this holds. So let me consider scalar product Px0, so projection of X onto X0, scalar product with Y. I recall that X is a direct sum of X0 and its orthogonal complement. And this means that for any vector X and Y in X, we may represent them as follows. So X is equal to orthogonal projection onto X0 plus X minus orthogonal projection to X0. The same for Y, orthogonal projection of Y plus Y minus orthogonal projection. And so these objects, they belong to this set. And these objects, the other objects, and these objects, they belong to this set, that is, they're orthogonal to X0. Hence, I may decompose Y here as here. And now, then the scalar product of this guy with Y is equal to scalar product with the first summand so with the first summand, and here plus scalar product of this guy with the second summand. But the second summand is orthogonal to X0, and this guy belongs to X0. So the second part, so the second scalar product will disappear. Okay?
Okay, it's clear.
Plus 0. Okay, but we can do the same consideration and say that it is the same as this guy. That is, we have this. Of course, we may add this. And scalar product of this guy with this guy will give 0. Okay? Is it clear?
Yeah, it's very clear.
Perfect. So we have a very nice example of a self-adjoint operator in an infinite dimensional Hilbert space. So orthogonal projectors, they are infinite dimensional. Okay, so actually, we are quite slow today, but let me still present you one theorem with a very short proof, but it's an important theorem. So it takes 5 minutes more, okay? I hope you will survive 5 minutes more.
Okay.
So theorem, so let X be a Hilbert space, A be a bounded linear operator on X, then the closure of the image of X under A is just the orthogonal complement to the kernel of A star. And here the dual statement that if we have A star instead of A here, then here we have A instead of A star. So this A of X bar is orthogonal complement to this guy, and hence X can be represented as a direct sum of this kernel of this space, so this space, and its orthogonal complement. So one implies two immediately. So from here we have this direct sum, from here we have this direct sum. In particular, if A is self-adjoint, then from this formula we just forget the star and we get that this set is orthogonal to the kernel of A, what is written here. And this sum, X is represented as a direct sum of this guy and this guy without star. Okay, so actually here we have to show this and this. Okay, but proof is very easy. Follows exactly directly from lemma 8.5 and theorem 6.10, which was Riesz representation theorem about Riesz isometry. Namely, from lemma 8.5 claims that this guy is just the space, the set of all y such that we have this statement. This is a lemma 8.5. And now using this representation theorem, we know that all continuous linear functionals act in this way. Okay, so this everything here follows from lemma 8.5. Agree?
Yeah, agree.
Okay, and now similar how to prove it. This statement in a similar way. Just we use A star as the original operator, and we use A2 stars as adjoint to A star. And we are in the setting of Hilbert spaces, so we know that A2 stars is nothing else but A star, just R, without stars. So we just repeat all argumentation with this situation. Okay, so that's it, in the sense that we have proved this theorem, and it is important. So I use just 2 more minutes to explain the importance of this theorem. It is given in this remark. So let X be a Hilbert space. A is a bounded linear operator. For simplicity, let us assume that this A of X is already closed, so we don't need this bar. So the closure is A of X itself. The image is closed. We consider such equation where y is given, a is given, x is unknown. So this is an equation. And the equation is solvable if and only if the right-hand side belongs to the image of x under A. That is, there is an element x in x, which is whose image is y. And now here, using this theorem which we have just shown, this means that y is lives in the orthogonal complement to the kernel of A star. What does it mean? What does it mean? It means that for any y star from the kernel of A star, the following holds. In some cases, it is easier to find this set than to find this set. Furthermore, so let A of x be closed and let A star be injective. So what does mean that A star is an injective operator? This means A star is a linear operator. So A star is injective means that the kernel of A star is just one element, a region, so zero element of the vector space. Yes, for linear operator, injectivity means exactly this. So there is only one element in the kernel, zero, which is that's it. But what does it mean? This means that if this holds, this means that orthogonal complement to this set is the whole space X. Hence, this means that the A itself is surjective. A is surjective. That is, we have this. That is so. If we show that A star is injective, we show that this equation is solvable for any x in X. So this is one application. On the other hand, if this operator A is surjective, then it is an open mapping by the open mapping theorem, and hence we also have some nice properties which we have discussed in chapter 5 or 4, or somewhere before. But nevertheless, you see, so the idea is that sometimes the investigation of the adjoint operator help us to get some good properties of the original operator A, in particular to solve some equations. Okay, so I guess that's it for today. If you have questions or comments, you're welcome. And we continue then with compact operators. We continue next time.
Okay, I want to add a comment.
Yes?
I want to say something about today we discussed an example about the left shift operator and the right shift operator.
Yes?
Actually, I want to say that these two operators is much more powerful maybe than what I thought before, because uh, in the future study, for example, in the Banach algebra, there is a theorem called the spectrum of the elements in Banach algebra is not continuous but semi-continuous, and the proof just use the uh, right shift operator, but with some different weights. Today the weight is all 111, but we need to slightly modify the weights, and this method is so-called Kapitani shift operator, and it's also interesting.
Yes, yes. And also the word Kakutani is somehow related to the dual to the theorem Riesz-Markov-Kakutani about the duality between different spaces of functions and measures. So in your discrete case, of course, there is a measure behind this shift with weights. But okay, this is just a long discussion. We don't need to discuss it. Of course, we discuss some simple, basic things, but they are actually like a kind of canonical things in the sense that more advanced. So it is a usual situation where a big class of some general objects can be represented using some finite amount of building blocks, and these building blocks are just, so to say, basic canonical objects. Yeah, for example, I don't know, even on the level of processes. So what are Levy processes? It's a kind of a mixture, in roughly speaking, it's a mixture of Brownian motion and Poisson processes, but mixture in a proper sense. Okay. And this is a typical situation everywhere. And concerning the spectral theory, we will say if you just a few words. So of course we don't go to Banachal algebras or whatever, but a few words about spectral things, it is supposed to say something. But actually, I thought that we do more today, but probably we still need more than one lecture to finish the course. But let us see. Let us decide it after the next lecture. So we will see how much we make, and we decide how we do further. Okay, are there any further questions or comments? Okay, then I stop the recording first.